Welcome everybody to the last talk today. Last talk will be given by Gennian. Gennian received his PhD in mathematics from Suzhou University in 1996 and is currently at the Capital Normal University. Gennian studies problems related to core structures in design theory, and what strikes me when I changing to this one, and I'm looking at the papers Gennian has published. Then he has a skill in applying designs and other discrete structures to engineering. And the titles of his papers contain keywords like quantum codes, multimedia fingerprinting, compressed sensing, frequency hopping, radar arrays, optical networks, traffic grooming, authentication. And many of his papers have appeared in the top IEEE journal, IEEE Transactions on Information Theory. And he has published well over 100 papers, and for his work he received the Hall Medal in 2006, and he has also received many Chinese awards. And today he will talk on sparse hypergraphs from theory to application. Please.
Thanks, Chair Patrick, for the introduction. First, I need to thank the organizer to organize such a conference and give us a chance to speak here. And before I start, I need to say a few words to Charlie. And first met Charlie in 1993 in Shanghai conference when I was a student in Suzhou University. And after that, we communicated quite a lot, and Charlie visited us, I think, more than 20 times in China. And I think probably Charlie is the most, one of the combinatorics who visit China most often, and gave us a lot of help, especially not only for me and others for the Chinese community or for the design student. So thank you, Charlie, and happy birthday. And the topic I will talk about is on sparse hypergraph and with some applications. And the topic is the problem is the typo Turing type graph problems. And the work was done with my former PhD student, Wen Song and Xin Wang. Here is the outline of my talk, and I will talk about some conjectures in sparse hypergraphs. And I will also talk the connections with hooked and separated families. First, let's look at some notations we will use. We will talk about, we choose some elements with n size and form uniform hypergraphs. And that means all the size of the hyper-ATs will be the same with R. And we take a subgraph from the hypergraph and look at how many, we just take the EATs and look at how many vertices these EATs will cover. I mean, the cover, that means all the vertices, they will have degree at more than one, at least one. If you put in some isolated vertices, then we can also look it as a subgraph with EATs. And we'll use this notation to denote all such subgraphs with E edges and which are covered at most V vertices. Now the problem is that we will try to form a hypergraph which will satisfy such property that any E edges they will cover at least V minus 1 point. That means that in this graph, any subgraph which with E edges and only covered V vertices will be forbidden in the graph. All such subgraphs will be get together in here, and then we'll be interested in that how large will that of the edges of the graph satisfy this property. That means we'll discuss about the maximum number of edges in the uniform graph that satisfy that any E edges in the graph, they will cover at least V minus 1 point. They get me for the problem? And okay. And the problem is that means that if we take an empty graph, then any E edges will cover no points, right? So then you can always satisfy this property. And then you can bring or you can add more edges into the graph. You're starting just from an empty graph and add more edges out. And one and more edges. In some states, you will find that in the graph there will be some substructure with E edges only cover 3 points. So that's the critical number. There is a critical number between these in the edges process. Then we will discuss about what is the most large possible number of this function. If we've just fixed some parameters R, V, and E, and then this number will be some function of these parameters. And we'll look at the magnitude of such function when the number of the points approach to infinity. So let's look at some history about this problem. In more than 45 years ago, and from an Einstein source, proved that if the subgraph has E edges and covered only this number, E times R minus K plus K points, and then all the number of edges in the in the whole hypergraph will be about the magnitude with this number A to the K. And they conjectured that if we put one more point for the subgraph, that means we have E times I R minus K plus K plus 1 points with this, also this E edges. Then the number of edges will decrease, right? Will decrease. You can think about it, because the requirements will be more strict. You cannot allow such graphs appear in the graph. So they conjectured that A to the keys will be the up bound for such function. And also it is possible you can find some hypergraphs, and with the number of the hyper edges as large as possible to approaching to A to the key, just a little bit less than K. That means you can find some hypergraphs. The number of the hyper edges can be as large as possible, but you cannot over A to the keys. That's the conjecture. Let's just look at a simple example. If we just take R equals 3 and take 3 edges, that means we just take some triples. And we just take 3 edges. And the K, in fact, is the intersections of the edges, between edges. And K equals 2. And the problem will be exactly this one. And if we use a table to characterize that, and each column is an H, is a half H, and you can see that any 2 half H will intersect exactly 1 point. And all these three half H just covered exactly 6 points here. This is a substructure, a particular substructure. And for these conjections, we will look at the up bound and the low bound. And for all the known results, the tight bounds, that means this condition satisfied for these cases is quite rare up to now. After 3 years, Luther and the Meridi proved this special case, which is now called 6-3 series. That means the conjecture, the general conjecture, it holds for these parameters. And up 10 years later, they generalized the size of the half edges from 3 to general R. And 20 years more later, they generalized the intersections from K to any K. All these known results are just about the number of the edges with only 3. That means E always equals 3. That's the only known result up to now. Besides these exact bounds, we also interested in the up bounds and also some special lower bounds. For the up bounds, we have this for more than 3 edges. For the 4 edges, the conjecture for the up bounds holds. Now we just state the conjecture again, and we mean that we look at what is the magnitude of the number of the hyper edges with the property that any E edges will cover at least this number of vertices. And we already see that this conjecture is true for the number of the edges, the subgraph, just 3 edges already known. And also we have some asymptotic. Besides this, we also have some asymptotic bounds, up bounds. That means that the number of vertices in the subgraph can be a little bit over 1. This number is a little bit over 1. so a little bit loose, then you can still, if you can still get some up bounds, the result will also be interesting. So for the exact up bound, we still have this special case. That's all the known results we have now for the exact lower bound and upper bound, and asymptotic ones, and some special cases for the conjecture. So what we have done for this this conjecture that we got that we prove the upper bounds for the conjecture will always be held when the parameters meet this property, which implies that all the known upper bounds will be covered by this new result. For the lower bounds, we just say that the only known result is for 3 edges. We get some more result on the first known general result for the number of the edges over 3, and we get some more edges for 4, 5, 7, and 6, and 8. But we cannot get the exact one for 6 edges. We also got some asymptotic result. How can we go to the new bounds? We mainly use this lemma called hypergraph remove lemma. The lemma says that if you try to form a hypergraph and with some forbidden substructures, and then you can just delete the edges up to some empty one, then the structure can be whole. And if you have to delete such a number of the edges such that the deleted graph can meet the property, that means the graph will not have the given forbidden subgraph. If you have to delete so many number of edges, then this lemma will tell you that the formal graph in fact have at least this number of copies of the forbidden graph G. That's the point of the lemma. We just use this lemma and use some techniques to get this new result. That's for the up one. But this up one covered all the known results up to now. And we use the same technique to get some more asymptotic result. That means the number of vertices for the forbidden graph will be a little bit over this number. I mean that will be a little bit more than I vertices, and I satisfy this equality. And this result, in some cases, is a little bit better than the non-asymptotic ones. Say, for this case, the conjecture said you can only have 10 times minus 3 plus 4, now the 80 vertices. But this asymptotic one can give you that you can get only 5 and 1 more point between the difference. And the former one, you have to 6 more vertices. And all these results are got from the hypergraph remove lemma, the technique. But I will not show you the details here. And you can approach to the papers on the archives. And for the lower bound, if you just give you some number ages and some the V and E, the forbidden structure, you can have many types of topology structures. So if you try to form a hypergraph to rule out all such kind of substructures, it's a mess. You have to check one by one. So we try to get more strict properties. That means we try to rule out try to construct some hypergraphs to satisfy a little bit strict properties. This strict property is that we try to rule out some particular structures. This particular structure is a little bit stronger than the requirements for the V and E properties. So the property is that we call rainbow K cycles. That means we take K edges and take K vertices, and these vertices and edges are connected one by one in some order. And if we can participate the number the vertices in some distinct parts, such that all these vertices appear in distinct parts, and then we will call this both cycle has some rainbow property. That's in fact is a coloring process for the vertices. We look at one example here. Here is a rainbow 3 cycle, and we have 3 edges here, and we participated the vertices in more than just 3 parts, and these any points and edges will meet the rainbow K-cycle property. And here is another one with the property for 4 cycles, and you can check these edges and the vertices will satisfy the rainbow property. And we should observe that if a hypergraph is rainbow 3 cycle free, that means that it does not have any rainbow cycles with length 3, then this hypergraph will be will be free of all such kind of subgraphs. And we use these properties. We just count the number of the edges and the vertices in the conjecture, and you can find that if the subgraph satisfies some properties that it cannot contain some length of rainbow cycles, then you can rule out all such substructures in the hypergraph. That's exactly what you want in the conjectures. Then we try to construct the hypergraphs which has no rainbow cycles with length 3 or 4, and then we can meet the property. How can we get such a hypergraph? We just use additive number series problem, and it's quite complicated here, so I will not here. And just use these observations, we can improve the lower bounds. especially for the number of the edges over than 3. Okay, that's what we already done for the sparse hypergraph conjectures. And also we can find that these results has a close connection with some applications, especially hash families and some other coding-related problems. The following I will introduce is perfect hash family. A perfect hash family is a bunch of discrete functions over some alphabet with Q elements. And if we just form the functions, to write down the functions as a table, we use the functions to label the rows, and you use the elements to use the columns to label the columns, and that means each row is a function. The perfect function means that if you take any two t columns from this table, then you will find at least one row. This row can separate all these t elements. That means all these elements in these positions will be distinct. That's called perfect hash families. The problem that we are concerned that if you fix the number of the functions and we try to find the maximum number of the columns of this table, and we will use this notation to denote it. And then this will be a function of this the parameters with the stress t and the number of the functions n and the alphabet size q. Put functions have many applications. I don't know mention here. And we'll be interested in that if we fix the number of the functions n and what is the maximum size of the columns, we have the up bound and asymptotic up bound and lower bound here. For the case with n is divisible by t minus 1, these bounds are exact. But how about the case with a is not divisible by t minus 1? And Chai-Kerwin posed this conjecture in 2007. For the special case with t equals 3 and the number of the functions is just 3, and they conjectured that this function cannot be over due to the truth. And some known results show that we have this one, and some probabilistic method, you can get the number of the vertices, the columns can be at least this number. And Professor Fujihara improved this one, used some finite geometry method. You can see from the shoulder from 2 to the over 3 to 3 to over 5, but it's still less than 2, right? The conjecture is that can you prove that the number of columns cannot be over q to the 2th will approach to 0 when q approach to infinity. And you can also try to construct some functions which can have as many as these columns. So how can you prove this conjecture? So So if we take a new viewpoint from hypergraph, sparse hypergraph viewpoint, you say that the conjecture of Charlie, let's say that you just look at three by n tables, and any three rows, they will, if they has some separation property, then any three columns, and you just regard the columns as a half age, of the hypergraph, and then the positive hash requirement will be that if the property that cannot be held, then any function we cannot separate these fixed three columns. That means any row will have at least two elements that are equal. They cannot be separated. So that means any row will cannot be separated, and then at least the two identified elements will appear here. Then that means that all these elements here, you have 9 elements, but each row has repeat of elements here. Then you can get at most 6 distinct elements. So that means that the Charlie's conjecture is just exactly what is we just say is called 6-3 theorem. You can use 6-3 theorem to recharacterize this the problem. Then you can get the conjecture is done. So it's quite straightforward. But if you try to do more for, say, t equals 4 or 5 or more, then you cannot use the 6-3 theorem again. So you have to find some more tools to put forward. So these conjectures on these problems. And if we just generalize the problem from positive hash family to more general case for separating hash family, that means the requirement will be not just exactly T1 columns. We switch from one column to more columns in each group, but the requirements are almost the same. That means that if we just take T groups of column, and the separating property requires that the functions will satisfy that we always, if we take any T groups, and we will find at least one function, they can separate all these results. The same problem will appear in similar to perfect case. So we'll look at this problem is posed by Dr. Stinson and others in 2008. And we will, similar with the perfect case, we'll look at these functions. That means we call the maybe we just denote the size of the columns as some type, and for the pocket case, all the wi is equal to 1. Here maybe more general, and we will denote all the summations of all the size of the columns we choose as U. Then we have the similar problems we will meet. That means we have such lower upper bounds and lower bounds. So how can you prove the special case is when the number of the functions is not divisible by U minus 1. When this probably can be meet, and then these up bounds and lower bounds can meet. For these general problems, I just mentioned that for the special case with t equals 3 and the type is 1, 1, 1, that's just the particular case of perfect hash family. And this is Charlie's conjecture. We can use the 6-3 theorem to prove that. Besides this, we can also use the tools from Sparse hypergraph, and to generate the result from 3 to 4. And the up bounds can be obtained from the hypergraph lemma properties, and the lower bounds can be constructed from the additive number theory. And these results already know in this paper, and but for the general separating case, how about the first special case with type 2, 2? We just only 4. The summation is only 4 for the types. And for this special case, and we can prove that the number of the columns will be this. How can we get this? The up bounds you just form or take 4 columns and regard it as half each. And then the separating properly will just say that use the hypergraph lemma. If you can have such number of hyper edges, then you will have some lemma 4 cycles inside, and then that means these functions cannot be separate on these 4 columns. You can check that. Just very simple properties you can get from the hypergraph lemmas. When you got this new up bounds, and then you can get some general result. That you can check that for the 4 columns case, these inequalities can be held very trivially. And then if these hold, then you can solve all the 4 columns cases. So the problem with that, how can we got a more general asymptotic bounds for some general case, not just 4 columns, when the number of the functions is equal to the summation of the type. Then we can get some more general result. How can we got that? We need some recursive bounds it's quite simple. We call that a Johnson type bound. How many minutes? Oh. And this property, how can we got this general recursive bounds? We just start from the check some rules, and we put all the distinguished vectors with length L. We put all the distinguished vectors to the left. If we just check from the left to the right, if the vectors in these L rows does not appear, then we shift to the left. Otherwise, we just put it to the right. That means we take out all the distinguished vectors in these L rows. This number, all these numbers cannot be overqueued to the L. And then what's left in the right column and right side, then you can check that this right side will satisfy these properties. That means the number of the columns will be one less in one column. Why? If this small table cannot satisfy this property, then that means each row in this table will violate the separating property, and each row, that means in all these remaining rows cannot satisfy the separating property. And then you just look at any, say we just take W1 minus 1 column from the first part, and then we just take one column within this part. Then these vectors of length L vector will appear in the left side, right? Because here is all the distinct vectors of length L. So that means this column cannot be separated in all these L rows. Then you get a contradiction. So use this just the reductive. We can reduce that, get some recursive method, and then you can prove that if the types, the summation of the types with U, and you can divide the number of the rows or functions by U minus 1. You take the residue R, and you can get this up bound very trivially. And this new up bound will be a little bit better than the low ones. And this simple recursive process can be used in the general case. With the number of the rows, we just be the summation of the type. For this result, a lot of works has been done. Previous known up bounds will be this one, and some works is focused on the main parts, and some other papers focused on the linear parts. And but the general result, the up bound should be. That means the exponential will be less than 2. So how can you get that? We just look at it. We can get this general new up bunch. That means the proof is quite simple. Let's look at if for t larger than 3 case, that means the different types has more than 3 columns, the type, and we can just look at, take 3 rows out, these 3 rows out, just similar to here. We can leave 3 rows out here, and all the remaining case is just 1 row, 1 row, 1 row. Use this reduction. That means we can choose L equals 1, U minus 3 times, and the remaining 3 rows will be this in the right places, and then use the simple recursive process. You can get this one. And already you know that this has been proved cannot be over to Q to the truth. So the summation cannot be over to Q to the truth. And for t equals 2 case, we just leave 4 rows and use the same process. We can get this new up bunch, and this up bunch is quite general. But you should note that when the type is exactly 1 and U minus 1, the up bunch is not, it can be a little bit larger, and Brackman already proved that result. And in this topic, we find some interesting problems in the Sparse hypergraph lemmas, and we got some new up bounds and lower bounds, and also find some new applications. One I just mentioned in separating hash families and post hash families, and we also find some more applications in coded caching. We established some connections between sparse hypergraph and PDA in coded caching problem. And tomorrow, to Min Chuan, we will talk about coded caching. But actually, we can also use the theory from sparse hypergraph to attack such problems. And I think I should stop here.
Thank you very much. We have a lot of time for questions. Everybody get out. Okay, if not, then let's thank the speaker again.